third quantum number, that is magnetic quantum number, represented by a small m. This is also known as orientation quantum number. It is denoted by the letter m. Zeeman found that when a strong magnetic field is applied to a source of a spectrum, each spectral line gets split up into a number of separate lines. This phenomenon is called Zeeman effect. If the spectrum is viewed in the same direction as the applied magnetic field, each line is seen to be split up into two components. Both of these are found to be circularly polarized but in the opposite directions. If, on the other hand, the spectrum is viewed in a direction at right angles of the magnetic field, each line is seen to be split up into three lines. The middle line is polarized in a direction parallel to the magnetic field, and the other two lines are polarized at right angles to it. The additional lines differ only slightly in energy from one another as well as from the original line, which appears alone in the absence of the magnetic field. In order to account for the additional lines which appears in magnetic field, it becomes necessary to have an additional quantum number. This quantum number is called magnetic quantum number m. If the total quantum number of the electron is h by 2 pi, then h by 2 pi gives the components of the total angular momentum in the direction of the magnetic field. If this component is quantized, the total angular momentum h by 2 pi can have only a definite possible inclination with respect to the direction of the magnetic field. Suppose the azimuthal quantum number is 2, then the number of possible inclination would be 5, that is 5 different orientations in space are possible. Such a behavior is called a space quantization. The corresponding m values are +2, +1, 0, -1 and -2. The possible values which m can have depend upon the total angular momentum, that is, on the azimuthal quantum number L. For any value of L, there are 2L plus 1 values of m. These ranges lie from -L through -1 through 0 to +L. This making a total of 2L plus 1 values. If L is equal to 0, that is the subcell is S, there is only one value of m, namely m equals to 0. If L equals to 1, that is subcell is P, m can have three values, that is m equals to 0, m equals to 1, then 0 and then +1. Similarly, if L equals to 2, m can have 5 values, that is m equals to -2, -1, 0, +1 and +2. Thus S subcell will have 1, P subcell will have 3, D subcell will have 5 and F subcell will have 7 possible values of m. The electron having the same value of n and L but different values of m will have different energies. However, these energies differ only slightly from each other. Now the next is fourth quantum number, and that fourth quantum number is a spin quantum number represented by S. It defines the angular momentum of the spin of the electron. It is denoted by S. It arises from the spectral evidence that an electron in its motion around the nucleus is an orbit, also rotates or spins about its own axis. The electron can spin clockwise or anti-clockwise. Therefore, two values of S are possible. Since quantum numbers can differ from one another only by integers, S can have the values plus 1 by 2 or minus 1 by 2 depending upon whether the electron spins one direction or in the other. The two values are generally written as plus 1 by 2 and minus 1 by 2. So there is a summary of 4 quantum numbers describing an electronic energy state. Let's see one by one. So first principal quantum number, its symbol is n and allowed value is 1, 2, 3, 4 dash infinity. Its function governs the energy and size of the orbital. Second quantum number is azimuthal or subsidiary. Its symbol is L and allowed value is 0, 1, 2, 3 dash n minus 1. Governs the shape of the orbital and the electronic angular momentum. The third quantum number is magnetic. Symbol M. Allowed value is plus minus L, that is from plus L 0 to minus L. Governs the direction of orbital and the electrons' behaviors in a magnetic field. And the fourth quantum number, that is last one, spin. Symbol is S and allowed value is plus minus 1 by 2. Governs the axial angular momentum of the electron. Now let's see Pauli's exclusion principle. W. Pauli in 1925 enunciated his famous rule, which is known as Pauli's exclusion principle. This rule states that no two electrons of a particular atom can have all the values of 4 quantum numbers same. Thus, in the same atom, any two electrons may have 3, n, L and m quantum numbers identical, but the fourth S must be different, that is, a spin quantum number must be different. So, understand this with illustration. Consider helium, that is He, has got 2 electrons. For both electrons of helium, n equals to 1, L equals to 0, m equals to 0, but its spin will be plus 1 by 2 or minus 1 by 2. Thus, the value of fourth quantum number is different. For both electron, that is first and second electron, n value is 1, 1 and L value is 0, 0 and m value is for both electrons 0 and 0, but spin value is plus 1 by 2 and minus 1 by 2. The principle is very useful in determining the maximum number of electrons that can occur in any quantum group. The application of the exclusion principle may be illustrated by serving the maximum number of electrons which can be contained in any orbit or cell. Jai Bajrang Bali, Jai Sankat Mocha.